Okay, so we left off last time doing some Lewis structures of a number of different molecules, and we were basically following the rules we were given earlier in that lecture. And so the rules, of course, are this set of rules here where we're finding the total number of valence electrons, we're drawing the atoms and the bonds to the atoms, and each step that we draw bonds, right, those are representing electrons, so we subtract those electrons from the overall total, complete the octets of everything, and we're good to go. So we'll have a lot of practice with this in the lab that you're doing on Monday. We did find that there are some exceptions to the octet rule for hydrogen, helium, beryllium, boron, aluminum, and those all have incomplete octets where you don't actually have to have 8 electrons around them, but you can also have elements that have expanded octets or can have more than 8 electrons around them. But you'll also have some species that don't have octets just because there's an odd number of electrons, and that's okay too. So we finished off doing a couple of those exceptions, right? Beryllium and or beryllium difluoride and sulfur hexafluoride. Actually, sulfur hexafluoride is one that I like because it's kind of a neat thing. It's actually a gas that's used in a variety of different applications, but it's a very dense gas. It's actually heavier than air. It does some pretty cool things. And if we have time, at the end of this chapter, at the end of the term, to show you kind of a fun video, or you can Google sulfur hexafluoride. There's some pretty cool things with that. But anyway, we did the Lewis structure of that one, which of course the sulfur hexafluoride is an expanded octet, and the beryllium difluoride has a central atom with an incomplete octet. So we got a couple other examples. So the boron trihydride. So we'll go through the process here again for figuring out the Lewis structure. And so the first thing is we've got boron. Okay, so boron has a total of 3 valence electrons. And hydrogen, where we have 3 hydrogens, and each hydrogen has 1 valence electron. And so we have a total of 6 valence electrons in the boron trihydride molecule. And so we have our boron in the middle because in the Lewis dot diagram, we have boron has 3 valence electrons, so 1, 2, 3. And hydrogen would only have 1, so the boron is going to be our central atom, so it goes in the middle, and we put the hydrogens around it. Then we draw in a bond from each of the surrounding atoms to the central atom, right? And so that takes up, well, there's 2, 4, 6 electrons because there's 3 bonds, so we subtract off our 6 bonding electrons. We have no electrons remaining, and the thing about the boron is the boron only has 6 valence electrons, but it's okay because that's one of our exceptions to the octet rule. So there's boron trihydride. Then if you look at nitrogen monoxide, right? So nitrogen, so it has 1, 2, 3, 4, 5 valence electrons. Oxygen has 6. 1, 2, 3, 4, 5, and 6. And so the total number of valence electrons in this next example, the nitrogen has 5 valence electrons, the oxygen has 6, but there's only 1 of each. And so you have a total of 11 valence electrons. And so here you only have 2 atoms, and that's okay. It just means that they're going to be placed next to each other. It doesn't matter. They're not really a central atom if you only have 2 of them. So we have our nitrogen and our oxygen. And we're going to start out here by placing a bond between the 2. And then when you do that, you can subtract off the 2 bonding electrons. Okay, that leaves 9 electrons remaining. Okay, now this is going to be one of the things, if we go back up to the set of rules that we have, we're going to find something interesting in here that we haven't done yet. And that's the rule number 4 here, completing octets. So we're going to assign those remaining 9 electrons in this, okay? And then we're going to find, so this is sort of rule B here. If an atom doesn't have an octet, you're going to move electrons from a lone pair of bonded atoms to form a multiple bond. And you can do that more than once in a lot of cases, okay? Now, here, we're still not going to have full octets because this is one of our exceptions, but this is something where we're going to want to get as close to an octet as we possibly can. So we've got 9 electrons to place. We're going to start placing them on the oxygen because it's more electronegative. So we put 1, 2, 3, 4, 5, 6 electrons around the oxygen. That gives this oxygen an octet now. We only have 3 more electrons to place, so we go 1, 2, and we're going to start putting them in pairs each time we do it, and then we're going to have the 3rd electron here, right? And that takes care of our 9 electrons, and we're good. Except for if we look at so the oxygen has an octet. That one's great right now. The nitrogen doesn't. Okay, so what we're going to do is we're going to take a lone pair of electrons from the oxygen. So we're going to take this lone pair of electrons here, and we're going to move it over there, right? If we look at the nitrogen has 1, 2, 3, 4, 5 electrons around it, right? So I'm going to take that lone pair and put it here. So when I draw the molecule again, I've got a double bond between the oxygen and the nitrogen. I have 2 lone pairs remaining on the oxygen, 1 lone pair, and that free radical, that unpaired electron remaining on the nitrogen. And now we actually have, so 2, 4, 6, 7 electrons around the nitrogen, and the oxygen still has 8. And so that's where you'd have the Lewis structure of the nitrogen monoxide. But that's the idea of taking a lone pair of electrons and making it into a bond. So I want to do another example of this, and this is for some carbon compounds, okay? Oh, I guess we should still do the formal charge for both of these. So we'll go back and do the formal charge for these first. Just make sure we're consistent on those. So if we go back to the boron trihydride, the formal charge of the boron, here, do this. Right, so if we do formal charges for the boron, right, boron has 3 valence electrons, minus 0 lone pair electrons, minus 1/2 of the 6 bonding electrons. That equals 0. And the hydrogen, of course, has 1 valence electron, minus 0 lone pairs, minus 1/2 of the bonding electrons to each of those hydrogens, so that'll be 0 as well. So we don't have to mark those at all. We will have to mark some in just a minute. If I look at the formal charges for nitrogen and oxygen, right, nitrogen has 5, minus, there are 3 unpaired electrons, okay, and then you can subtract off, so 1/2 of the 4 shared electrons. So here nitrogen is going to be 0 also, and oxygen will be 6 minus the 4 unpaired, lone pair electrons, or electrons that are not involved in bonding, minus 1/2 of those 4 electrons that are in the bonds that are being shared. So that's going to be 0 as well. Another example I want for you is when you have something like C2H4. This is called ethylene. This molecule will have 2 central atoms. And the 2 central atoms is common for carbon-based compounds. Okay, and so here you'd have carbon. Each carbon, if you just look at the Lewis diagram, has 4 bonding electrons, whereas hydrogen only, 4 unpaired electrons, whereas hydrogen only has 1. So what you actually wind up doing with this is you have 2 carbons here, and so you're going to just place the carbons next to each other. And if you had more carbons, you could put them in a long row, and then you're going to surround the hydrogens around them. Okay, so when we add up our total number of valence electrons, right, carbon has, I've got 2 carbons. Each carbon has 4 valence electrons. I have hydrogen, I've got 4 hydrogens. Each of them has 1 valence electron. So we have a total of 8, right, plus 4 gives us 12 valence electrons. Okay, now we have our atom with our molecule with the atoms all spaced around. We start drawing in the bonds. And so we're going to put a bond between those 2 carbon atoms. Those are my 2 central atoms in this molecule. And we're just going to take and think about them one at a time a little bit later when we start using this for shapes. But this is something that's common when you have carbon-based compounds. And we're going to draw in bonds to the surrounding atoms. And a good rule of thumb is have those hydrogens surrounding them somewhat with a little bit of symmetry here, though you'll find that as you get more familiar with doing Lewis structures, these will become easier. When you start getting, for example, more carbon-based compounds, you'll start to see a trends in how they're actually drawn. It takes a little experience, but that's what we're just getting started on it now, so you'll get that experience as we go. Now, this particular molecule, we've drawn in 5 bonds, so there's 2, 4, 6, 8, 10 bonding electrons. Okay, which leaves us with 2 valence electrons remaining. And so we're just going to go and place them on one of the carbons. Now, all of my hydrogens have 2 electrons around them, so they're all happy. The carbons, though, the carbon on the right has 2, 4, 6, and a lone pair for 8 electrons. The carbon on the left has 2, 4, 6, but it doesn't have a lone pair, so it doesn't have a complete octet. And so we can then go and move that lone pair of electrons from the carbon on the left and make a double bond, okay? And so when we do that, now we have the compound C with a double bond to the next carbon. And hydrogens here, hydrogen there, and a hydrogen there, okay? And if you look at the formal charges, okay, so the formal charges for the carbon are going to be, so 4 valence electrons minus 0 lone pair electrons minus 1/2 of the 8 electrons in bonds, right? There's 4 bonds to each of those carbon. And so, that should be 0. Writing the thing that I'm saying, not the thing, come on, what am I doing? There we go. Oops. So that should be 0. And of course, hydrogen again will be 1 minus 0 minus 1/2 of the 2 electrons bonded to each of the hydrogens. So that'll be 0. So you'll notice on carbon, there are 1, 2, 3, 4 bonds to each carbon, and that's a common thing for carbon compounds that you'll want to remember when you go on to an organic chemistry class. Okay. So the last thing that we're really going to look at as far as Lewis structures go is resonance. Okay, so resonance is when you have, again, there's more than one correct Lewis structure. Okay, and so we're going to talk about this. We're going to go through the rules. And once we have that more than one correct Lewis structure, we can consider what's called a resonance hybrid, which is a superposition of those Lewis structures. Essentially, you're going to have double bonds that move, or that can be in different locations on the molecule. And the actual structure for that thing is a hybrid of all 3 or 4 or 5 or 6 or 2, right, of the Lewis structures for these molecules. In the case of nitrate, we're going to have more than one possible Lewis structure. And this is where formal charges will come in a little bit too. So here, we're going to start out, we know that our nitrogen has 5 valence electrons. So there's 1, 2, 3, 4, 5. And oxygen, each oxygen has 6. 1, 2, 3, 4, 5, 6. Okay, so our nitrogen is going to be our central atom, and our oxygens will be the surrounding atoms. When we look at the total number of valence electrons, we've got nitrogen, okay, that has there's 1 nitrogen and there's 5 valence electrons. Oxygen, well, we have 3 oxygens and there are 6 valence electrons on each. But you also have, by the way, this negative charge.
Yes.
A negative charge means we add 1 more, so plus 1 more electron. If it were a positive charge, we would remove one of those electrons. So here, we've got a total of 5 plus 3 times 6, so 5 plus 18 is 23, plus another electron is 24 valence electrons, okay? So we're gonna go and place our nitrogen in the middle, our oxygens around it. Now, when we do Lewis structures, of things that have resonance, we're gonna make sure we keep our atoms in the same locations. So it's easy, so that you can depict where the bonds change, right? What atoms, how the atoms are bonded differs, not how the atom's position differs. And so here I'm going to say, okay, I'm going to lock in my oxygens on the left, top, and right. Okay, so I've now got my 4 atoms placed. The next thing I'm going to do is I'm going to draw one bond in between the central and surrounding atoms. And that takes care of 6 electrons. So minus 6 bonding electrons leaves us with another 18 valence electrons to place. Following the rules before, we're going to start placing them around the oxygens as pairs until we fill up their octets. So there's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So we've got 18 electrons now placed. That's used up all of our valence electrons. Now we need to go check and make sure everything has an octet. Well, all the oxygens have an octet. I just filled up their orbitals so that they would, right? There's 8 on the each oxygen, 8 on the oxygen on the left, 8 on the one on the top, and 8 on the one on the right. But the nitrogen only has 6 electrons. So we're going to use that same process, okay, that we talked about before, right? And we're going to take a lone pair of electrons, and it doesn't matter, right? You could take a lone pair of electrons from any one of the 3 oxygens. So what we're going to do, I'm going to go to the top one here, and I'm going to take that lone pair of electrons and move it into a double bond to form a double bond with a nitrogen, which now means we have a nitrogen double bonded to an oxygen. This oxygen up here has 2, 4 lone pair electrons, so 2 lone pairs. The oxygen on the right, it remains the same. So the oxygen on the left remains the same, the oxygen on the right remains the same. And we have a new Lewis structure. Now, if we do our formal charges, so now, by the way, the nitrogen has 2, 4, 6, 8 electrons around it, based on 2 double bonds and the 2 single bonds. So if we do our formal charges, okay, the formal charges on this, well, we've got nitrogen, which has 5 valence electrons, minus 0 lone pair electrons, minus 1/2 of the 8 electrons that it's sharing, because there's 4 bonds. So it's going to be +1. Okay, so if we have a non-zero formal charge, we come over here and put +1 on the nitrogen, just in parentheses there. But we now have 2 different types of oxygen. We've got the oxygen with a single bond, right, and 6 lone pair electrons. So that's going to be 6 valence electrons minus 6 minus 1/2 of the bonding electrons to it, which is 2. So those single bonded oxygen atoms are going to be -1 each. The double bond oxygen, okay, so I have to go, before I do the double bond formal charge, that means I need to go put a -1 on each of those oxygens that has a -1 formal charge. The other type of oxygen is a double bonded oxygen, 6 valence electrons minus 4 lone pair electrons minus 1/2 of the 4 electrons that it's sharing gives you 0. So the top oxygen has a no formal charge to it. Now there's a non-zero sum of the formal charges here, and I'm going to tell you if your nitrogen is if your nitrogen has a if your central atom is in period 2 or above, as soon as they have octets, you're not going to move electrons around, right? But you still need to keep track of the formal charges. If you add up the formal charges, we can put the total charge of this thing up and to the right when you surround that molecule by brackets, okay? And that total formal charge, the sum of the formal charges, right, should equal the charge on that, in this case, polyatomic ion. So now I'm just going to rewrite this molecule that we have, this nitrogen, this nitrate. I'm just going to rewrite it over here. Now, when you put a formal charge, it doesn't really matter where you put it, as long as it's right next to that atom so that you can really tell which atom you're labeling with the formal charges. So there's your nitrate molecule. But in this particular example, we took that lone pair of electrons from the top oxygen. What if we had taken it from a different one, right? What if we had instead taken it from, oh, let's say this lone pair instead to make a double bond there? If that were the case, right, we would have had a molecule that had the double bond to the oxygen on the left and the single bonds to the other two. Okay. Now these would have still been correct Lewis structures. But you would have to account for the fact that you can make these Lewis structures, right? Even though they're correct, they're fine. It's different than the first one that we did, right? But of course, if we took it from one of the other carbons, you could probably take it from the third other carbon, oxygen. Apparently my coffee's not kicked in, right? And you could have taken and made a double bond between the other nitrogen and oxygen. And so this would give you a different possibility for making the structure. So you have your in there, that would be a single bonded oxygen and double bonded oxygen. So these are the three possibilities you have for making this molecule. And they're all correct Lewis structures. And the only way they differ is in which oxygen is double bonded to the nitrogen. Okay, and I need to go and make sure I put in my charge overall on the other one. All right, so these right here are the three resonant structures of the nitrate polyatomic ion. And so those, the whole idea is these resonant structures differ really by where that double bond is. So if you were to look at the bond lengths and bond strengths of the nitrogen-oxygen bonds in nitrate ion, what you would find is none of the bonds are the same length and strength as a single bond. None of the bonds are the same length and strength as a double bond. They lie somewhere in the middle as far as their length and strength, because the actual molecule is a superposition of those three resonant structures. And so this polyatomic ion, nitrate, has three resonant structures that exist for it, and the only difference between them is really just where that double bond is between the nitrogen and the oxygen. So you can have all kinds of different types of resonance structures, and you'll find that you have a bunch of that as possibilities for when you do your Lewis structure lab. So we'll talk more about this on Tuesday when you do the Lewis structure lab, because you're going to have things like phosphate that, right, phosphate is directly below nitrogen, so it's period 3 or below. And phosphate is one where you can minimize formal charges even more. And we'll talk about that a little bit more on Tuesday. But this is the idea of resonance structures. Okay? And so that's where we'll end for today. Maybe we'll do phosphate at the very beginning on Monday so you can see it and understand that you can expand phosphate's octet because it's period 3 or below. Okay? So that's where we'll stop for today. And we'll pick up with VSEPR theory on Monday.